Okay. So so let's just get started with the basic concepts of momentum. So as you all know, as you hopefully all know, that if you have a particle with mass m, velocity v, then its momentum, which we usually denote as vector p, is simply mv. And then in this very simple one particle case, you can also write Newton's second law in the form F equals dp dt, because this is simply equal to m dv dt, which is just ma. Now, so this is the most basic case of just a single particle, but things get more interesting when you have a multi-particle system. So in that case, if I have a bunch of particles, let's say m1 to mn, with velocities v1 to vn, then you just define the total momentum in the same way. Sometimes say tot for total. Simply the sum of the momentums of the individual particles. Now, the interesting thing about this definition is that it interacts well with the center of mass, which is a common idea in many collisions problems and many momentum problems in general. So you can actually write this as, so here m is the total mass of the system, and VCM is simply the velocity of the center of mass. The center of mass is this geometric point, which is the sort of weighted average of the locations of the particles based on their masses. And the total momentum is simply like the momentum as if you view the center of mass as a single particle. So that's why this is quite a useful definition. If somebody has a question in the chat, can we say that the direction of the momentum will be the same as the velocity? So yeah, in the single particle case, that is indeed the case. In the single particle case, the vector momentum is defined to be m times the vector velocity. So this means that the direction of p and the direction of v are the same. That's just how vectors work. All right. So and then common idea in many problems is to look at the process in the frame of reference where the CM is at rest. So the CM is not moving. So we'll do a few problems with this idea, so you'll see what I mean in more detail later. Now, similarly for the system of particles, we have a form of Newton's second law, which just is that the net force on the system, so the net external force on the system, all the internal forces obviously cancel out due to Newton's third law, is simply the derivative of the total momentum. And this is sort of true in a more general context, more than just when you have a bunch of n particles. It's also true when you have a system where the mass is changing. So we'll see a couple of examples of this later on, but let's say you're sort of pulling some sort of cart and there's like sand coming into that cart. Then depending on how much sand is coming into that cart, you might have to provide extra force, because if you sort of have P, if you sort of just, this is a simplistic case, but we'll see in more detail later, but sort of have P equals mv, and then if now the mass is changing, then dp dt could be different than ma. Anyways, we'll see that later. But the point is that in the most general context, we have that in a system, the net force is the time derivative of momentum. Yeah. So somebody says, well, apply the product rule, then yeah, that's right. You apply the product rule. Just be a little careful in these kinds of problems where you have, let's say, sort of, you need to be careful to account for friction, and you need to make sure that friction isn't, let's say, an internal force. And if friction is an internal force, then there's no issue because it doesn't come up in the net force. But there are some cases where this is not super clear. And doing this sort of analysis would give a wrong answer. But the reason it's wrong is because you didn't account for the proper net force because there's some sort of subtle frictional or air resistance force, which is not internal and would sort of affect the problem. But in most cases, you can just sort of use this without any issue. That's pretty much all I had for theory. And I'm sort of assuming that you all have already seen momentum before a little bit, because if you're seeing it for the first time, it's probably better to do a bunch of really easy practice problems from some textbook in order to get yourself familiar before sort of doing physics contest problems, which tend to be much harder. So this is hopefully just a review for most of you. Most of you have seen this content before. But before I go on to doing some of the problems, let's just wait for a couple minutes to see if there's any questions about momentum and generally how to apply it and things like that. So just give me your question in the chat, and also feel free to unmute and just say your question. Just give it a minute. If the mass changes, then what will be the general strategy to tackle the question? That's somebody's question as well. I mean, we'll see an example of this later on. So we'll get to a problem which has this idea, but in general, from here you can see that dp dt is m dv dt plus v dm dt. So if the mass is changing, if some sort of mass is being added to the system, then if you know the rate at which the mass is being added, then you can find the force needed to sustain that dynamic. Good question. But yeah, we'll see an example. So like, which one is to be considered as a frame of reference? I don't really understand that question. Could you please elaborate? Which question? Like one where the mass is changing? Or in general? So I mean, okay, just about frames of references. You can use any frame of reference, any what do they call it? Inertial frame. Inertial frame is one that's moving at constant velocity. You can use any frame of reference and you should get the same exact answer in all cases. An idea for them. So what the masses change, the center of mass is much more tricky because you're sort of adding mass to the system, which means the center of mass. And analyzing the center of mass is usually very tricky. So there's not going to be many problems where you want to use the center of mass frame of reference in a changing mass problem. What is the difference between linear momentum and impulse? Good question. So we'll see an example of a couple of problems which deal with impulse. But just yeah, okay, this is a good question. Let me just say something about it. So what is impulse? So impulse, it's a quantity, has the same units as momentum, and in many cases, it's tracking something similar to momentum, but it's something more like, let me think of a good example. So the right way to think about it, so impulse and momentum are very similar quantities, but impulse, generally you want to think of it as a change in momentum. So if I provide so the units of momentum and all that are Newton seconds, or this is the same thing as kilogram meter per second. So if I say there's 20 Newton seconds of impulse, then I'm generally saying that I sort of change the momentum of an object by 20. And generally this is because we sort of view impulse as a sort of the sort of infinitesimal impulse as f dt. If you are applying some force on an object over some period of time, then you sort of apply an f dt impulse. And that means that the sort of, if this is the case, then the momentum changes by dj, simply by this relation up here. So if I provide a force F over a time dt, then the momentum of the thing I'm applying the force to changes by F dt. So somebody asked, would an instantaneous impulse be the same as an instantaneous force? Well, I mean, impulse and force have different units. They're sort of different quantities. But what we're sort of saying is that if I have there's no such thing as sort of instantaneous impulse. Every impulse that happens over some period of time, but that period of time can be very small. So if I provide a really large force over a really short period of time, then I can change the momentum of an object by some amount, which is the product of the force and the time, if it's a constant force. So an example of this is like if I have a wall and I have a ball which bounces against the wall and bounces back. What really is happening? What's happening is that for a really short amount of time, the wall is providing a really large force to this ball. And it's the amount of force that's needed to sort of change the momentum from, let's say, minus mv to plus mv, if it sort of bounces off elastically and after some time it sort of now is going in this direction. So the wall is providing a 2mv impulse to the ball. And the process for that is as the ball sort of hits the wall, it's sort of, there's a very short period of time where the wall provides a really large normal force backwards on the ball to sort of push it back off. Can we call momentum as impulse as the time becomes very small, the force remains the same? I'm not sure what that question means. Like, I think I basically said everything you need to know about impulse here. I think the only thing, like a lot of times impulse is talked about when the time is very small. The only reason that's useful is because there's lots of processes where a large force is applied over a short amount of time to change the momentum by a sort of reasonable quantity. Like this example of the ball bouncing off the wall. You don't really see the ball on the wall for a long time, but it is there, and there's a large force being applied there to sort of change the momentum. Another example of sort of using impulse to think about a process is like, this is a very common example, but it's sort of this car crash example. So if I have a car, I'm just going to draw a very simple model of a car. So a car, and it's moving at velocity v, and there's a wall, and it crashes into the wall. Then the total momentum change of the car is just going to be mv, because it sort of goes from moving at velocity v to being stopped once it crashes into the wall. Now, let's say you want to minimize the force on the car, because force is really like you want a less force on the car because you want the people in the car to survive. Then what you want is you want this collision to be done over a larger period of time, because we always know that the change in momentum is in a sort of simplistic model where the force is a constant function of time. Then And the way to sort of make the time interval of the collision longer is to sort of the engineering sort of idea is to take a section of the car front and make this section very, very collapsible. So that as it crashes into the wall, it sort of crashes all this distance over here. And that way the collision takes more time, so less force. Yeah, crumples on somebody's saying. So somebody's saying, from what I understand, impulse happens at an almost infinitesimal period of time. So how is it different than instantaneous force? Okay. So impulse happens at almost infinitesimal time. Well, that depends on what process you're doing. Like, you can have impulse over a long period of time. There's nothing wrong with that. But like I said, a lot of common processes have impulse happening over a short period of time. It's not an instantaneous force though, because like there's a force in play, but that force in the case where the impulse is over a really short period of time, but there's a sort of positive impulse, then that force is really, really large. So like if you have something which crashes into a wall and immediately stops, the amount of force on that object is going to be very, very large because the stopping happened in such a short amount of time. Okay. And can you repeat the collapsible part again? All I'm saying is that I don't know too much about the engineering, but people sort of design this section in front of the car to be very collapsible so that when it crashes into the wall, instead of just immediately stopping, like if the car was very rigid, right, it would immediately stop. But then the force will be really, really large because the impulse is the same, but the amount of time for the stopping of the car is very short. But if you have the front section of the car be collapsible, then the sort of car keeps crashing into the wall for a bit more time as the front section collapses a bit. And then you sort of decrease the time over which this collision, increase the time over which this collision happens, which means you sort of decrease the total force. So would impulse be m delta v? Well, sure. I mean, if the mass of the system is not changing, but generally it's better to think of it as a change in momentum. Like that's the best way I think about it. Somebody asked a question about geodesic on curved space-time. Must be acted upon a force, right? Okay, so somebody's asking a sort of general relativity question about momentum being conserved on a geodesic in space-time. This is definitely way above the content over here because sort of when you start working with general relativity, there's a lot more conservation laws and stuff become a lot more intricate, and I can't give a sort of good answer which I'm 100% sure about, and that would sort of make sense without the machinery of general relativity off the top of my head. This is something that you can sort of we can talk about later offline or something. But it's an interesting concept, but it's not useful for anything we'll be discussing today about geodesics and curved space-time. But yeah, so that's a good question. It's good to think about these kinds of things about yeah. Okay, lots of good questions. Any more questions before we move on? All right, looks like no more questions are coming in, so let's move on. So we'll go over problem one. So problem one is you have an astronaut who's 100 kilograms, and they're carrying a launcher, which is loaded with a 10-kilogram ball. and then this launcher fires. So this launcher has some sort of gunpowder or spring or whatever, and it launches this ball. And then after it launches this ball, what we see is that the astronaut and the ball they're both moving in some way, but their relative velocity is 50 meters per second. And the reason we're talking about relative velocity here is sort of, you imagine the astronaut is sort of floating in space and she fires this bowling ball. There's no way she can tell her own velocity, because if you're in space, there's nothing to reference your velocity with respect to. But all you can see is that, what's my velocity with respect to the bowling ball? Like, how far away is the bowling ball moving away from me as a function of time? It's the only thing the astronaut can really measure. So that's why we're told the relative velocity after the collision is 50, after the firing of the bowling ball is 50 meters per second. But the question now is, in this process, what is the impulse delivered to the astronaut? So in this process, it is true that the astronaut goes from not moving to moving backward with some velocity. So that's sort of an effective impulse, because if you sort of started at 0 and now you're moving backward with velocity v, then the impulse provided to you is mv. So the question is, just if you just know the relative velocity, then can you find the impulse provided to the astronaut? So I'll give everybody like 30 seconds to a minute to think about this a bit, and then we'll go over it. Somebody says the answer is 5. I don't think that's possible, because the units here should be in Newton seconds or kilogram meters per second. So maybe you just gave me the velocity of the astronaut. But even actually, the velocity of the astronaut is actually not 5 meters per second. It's not. So 5 is not even the velocity of the astronaut. Is everybody still here? Because for some reason my Zoom crashed for a sec.
Yes.
Okay, good. Yeah, hopefully the recording doesn't get messed up. But yeah, so some people are giving the right answer in the chat. So let's talk about it now. Yeah, so some people so let's see. So we have the mass of the astronaut's 100, mass of the bowling ball is 10, and we know that the sort of relative velocity is 50 meters per second. So if we say that the let's sort of say v1, v2. So we know momentum must be conserved. So that means that we must have m1 v1 equals m2 v2 for the total momentum to be conserved. And the total momentum is conserved because this is sort of a system of 2 particles, which is the astronaut and the bowling ball. And the only force that was done in the system was a sort of force in the launcher, like some sort of spring was unloaded or some gunpowder was fired. But that's an internal force. It applies on the bowling ball as well as the astronaut. So it's an internal force, and it doesn't affect it's not an external force. So the sort of dp/dt is the same, which means the momentum is conserved. So m1v1 equals m2v2. And then we also know that v2, or not v2 minus v1, in this case, it will be v1 plus v2 is vr. The reason is v1 plus v2 is because I sort of set it up where v1 is backwards and v2 is forwards. So the sort of relative velocity is v1 plus v2, if you think about it. So by the way, some people are pointing this out in chat. I've done something slightly non-standard where I've set the sort of directions of these velocities to be opposite. Generally, if you want to be more careful, you'd have to want to say v1 and v2 are both in this direction, and then one of them ends up being negative. But just for simplicity, I've said one of them is backwards, one of them is forwards, so that they're both positive. So this is the sort of system of equations that you get. And this is pretty easy to solve. Let's see, let's just do that real quick. So our goal is to find v1, so we want to substitute v2. So we get m1 v1 equals m2 or so v1 equals did I do this correctly? So then that means that sort of m1 v1, the total impulse provided is m1 m2 vr. And if you work this out, this is about, like, as somebody said in the chat, I think it's like 454 Newton seconds. Okay. So relatively simple question to start off, but any questions about this one? We'll just give it like 30 seconds, and then we'll move on to the next one. Can we say initial momentum is equal to final momentum? Yes, in this case you can, because the only force that was there in the system was an internal force of the launcher. If there's only internal forces, then the momentum is conserved. So yeah, you can say that. On what basis was I taking the direction of the velocity? Well, I can set it up however I want. Like if I had set up v1 and v2 to be both positive, or to both be sort of pointing to the right, then I would have solved it and I would have found that v1 is negative and v2 is positive. Just the math would tell you that. If I set up v1 to be pointing in this direction, then when you solve it, you get v1 positive, v2 negative. They're both the same exact situation. I just sort of set it up where implicitly v1 is pointing to the left and v2 is pointing to the right. But whenever you set up a problem like this, and if you set it up where v2 is to the right and v1 is to the left, and you get that one of them is negative, then that means that the direction was opposite. So there's actually you don't have to guess beforehand what the directions will be. The sign of the plus or minus sign of the answer will tell you what the direction is. But just for simplicity, I took v1 to be to the left and v2 to be to the right, because intuitively that's what should happen when this launcher is fired. So I know I expect the answers to be positive, but it's not necessary. I just did it because it's a little more intuitive in this case. Great question, though. It's a very, in general, I recommend if you're sort of getting wrong answers or you're getting confused with signs, take everything to be pointing in the same direction, and then let the pluses and minuses in the math sort out the directions for you. So if you're getting confused, just take everything to be pointing to the right or whatever. And then if you get that one of your v's is negative, then it tells you that it's pointing in the other direction. So usually it's best to let the math take care of it. But in this case, it was a simple enough example that I was okay with just having them be opposite. All right. Let's move on to problem 2. So in this problem, I have a cart of mass m moving at 12 meters per second, and I have a cart of mass 4 at rest. And these guys collide. They collide elastically. Now, technically, I don't know if we've gone over energy or not, but hopefully you all know what elastic collision means. It means that the kinetic energy is also conserved. No energy loss. So by the way, it's true that in a process where momentum is conserved, you can have energy loss. Because if the sort of internal force that was done in the process was a frictional force, then even though it's an internal force and momentum is conserved, it's still releasing away heat energy. So you can have energy loss but momentum conserved, but elastic collision assumes both are conserved. So anyways, in this problem, you have this, and then m after the collision is backwards at 6 meters per second. And you don't really know what happens with the 4 kilogram. It's just probably going to be moving, I'm just going to say, in this direction with some question mark velocity. So the question is, what is the velocity of the center of mass of the 2 carts before the collision? Now, one thing that is kind of funny about this problem, so what is cm velocity? This is an elastic collision. Before collision. So the interesting thing is that the center of mass velocity stays the same. Can somebody explain me why the center of mass velocity stays the same before and after the collision? The velocity of the center of mass. Just give a quick reason why. And sort of like the problem is kind of trolling in the sense that it said the center of mass velocity before. Hello, can you hear me? Am I here? Okay. So can somebody explain to me why the center of mass velocity is the same before and after? So somebody said no external forces, but why does that mean center of mass velocity is the same? Am I audible now, or am I still disconnected?
You are audible right now, but you were disconnected before, so I would appreciate if you could repeat.
Yeah, so I all I'm saying is why is the center of mass velocity the same before and after? I haven't really said anything beyond that. I'm just asking why that's the case. And somebody should stay in chat. Yeah, so good. People are kind of hitting on it. So because there are no forces on the center of mass because they cancel out. Yeah, pretty much. So the way I would say this is that we know that the momentum stays the same because there's only internal forces. And if you recall, you can write the total momentum as the total mass times the velocity of the center of mass. So if the momentum is staying the same, then the velocity of the center of mass is staying the same. So the question is just, what is the velocity of the center of mass? Now, somebody pointed out in chat, this is a problem which you can just grind out with some elastic collision formulas. Like m is one unknown, this sort of new velocity here, I'll call it like v1 is an unknown. And so you have 2 equations because you have momentum conservation and you have energy conservation. You have 2 unknowns, mass and velocity. You can solve it out. Okay, this is a bad approach though, because it's just you're not clear what's going on. Just you use some formulas, you solve, you say momentum is conserved, energy is conserved, and you just find what m is, you find what v1 is, and then you find what the center of mass velocity is. Okay, so that's possible. But let's sort of try to think of it in a more nicer way where there's less calculation. And it'll also illustrate a very important point about elastic collisions. So a very common idea in collision problems is to look in CM frame. So in general, let's just say I have a CM frame collision. So let's just do a very simple example. I have 2 objects of the same mass. And then in the CM frame, they must be sort of like this. Because what is the thing you know about the CM frame? In the frame where the center of mass is at rest, the total momentum is 0. That's the key property. So if I have two particles with the same mass and in their center of mass frame, they're going to be moving at velocity v to the right, and one of them velocity v to the left. So in the center of mass frame, what happens after the collision? And let's say it's not elastic. Let's say it's just a collision where energy could be lost, potentially. What can you say about what this is going to look like afterwards? Yes, they bounce off in opposite directions. And yeah, so in general, what happens is that they move at u where u is less than v, less than or equal to v. So they bounce off with equal velocity, but that velocity might be less. And it's less if energy is lost. If energy is lost, then the sort of bounce back velocity is smaller. If energy is conserved, then it's equal to v. But in this case, you can see that collisions in the center of mass stream are a lot simpler. Excuse me. And more generally, if I have m1, v1, m2, and this is in a CM frame, so I'm already assuming m1, v1 equals m2, v2, because this is what we need for the total momentum to be 0. Then they again, okay, so I'll sort of say they sort of bounce back with kv1 and kv2, where k is between 0 and 1, and k equals 1 for elastic. All right, so this is elastic collisions, especially, and generally collisions are very simple in the center of mass frame. So if we use this idea and go back up to this original problem, then let's look at what happens in the center of mass frame. So originally I had m at rest. So let's call the center of mass velocity equals v naught, and it's pointing to the right. In CM frame, does this make sense? So this is a very important step that I've made. Do people understand how that if this is in the original frame, and then I transform to the CM frame, then I get this sort of situation? No. So CM frame, so the way to think about the CM frame is sort of imagine I'm running along in this direction with velocity v0. So I'm running along the center of mass in this situation. Then to me, what does it look like? Well, it looks like the 4 kilogram is moving backwards at v0, because it's in the actual frame, the 4 kilogram is at rest. But if I'm sort of moving at velocity v0 to the right, then to me, it looks like the 4 kilogram is moving by v0 to the left. And similarly, if this is moving at 12 to the right, and I'm running along at v0, then it actually looks like it's only moving at 12 minus v0 to the right, to me. Because think about it, if I was moving exactly at 12 meters per second, and the m was moving at 12 meters per second, then it would look like it's at rest to me. But if I'm moving at, let's say, 5 meters per second, and it's at 12 meters per second, then to me, it looks like it's moving at 7 meters per second. Yeah, so CM frame is defined to be the frame where you're sort of running along with the center of mass. Yeah, CM frame is the one where we consider the CM to be stationary. So the sort of concrete way to think about it is you're sort of running, and you're running to sort of stay right next to the center of mass. And then to you, what does the situation look like? And physics works, because if you're moving at constant velocity and you're observing a system, then the physics is the same. This is Einstein had this very important observation where, like, if you're moving at constant velocity, then physics has to be indistinguishable, because it's an inertial frame. This is a very common idea in physics, to move into a frame moving at some different velocity, and then hopefully things become a little simpler. Anyways, So after, in the CM frame, so now after collision, in CM frame, now the M is moving backwards at 12 minus V0, and the 4 kilogram moving forward at V0. Make sense? Shouldn't be V1? What is V1? I never defined V1, right? Oh, V1, well, okay, sure. But I'm doing this in the center of mass frame. So in the center of mass frame, if I have two things moving towards each other, then like I said, in the elastic collision case, they simply just reflect off of each other in the center of mass frame. So because it's an elastic collision, the velocity is just going to be exactly reflected because I'm in the center of mass frame. The idea is I'm working in the center of mass frame. No. It's not because the masses are equal. In general, if I was in the center of mass frame, I have two things coming over like this. Then when after the elastic collision, they simply reflect off of each other. Notice that momentum is conserved. In this case, the momentum is 0. In this case, the momentum is 0. Energy is conserved. The kinetic energies are exactly the same. So elastic. In elastic collision, if you only in the center of mass frame, if you're not in the center of mass frame, this does not work. But in the center of mass frame, elastic collision means the velocity simply reflects. This happens in the center of mass frame only. But that's why center of mass frame is useful. So now let's look at after collision in original frame. So this is sort of what you sort of view in the collision if you're running along at V0 to the right. So what does that mean to somebody who's on the ground? Does this make sense? This is the same idea. Like when we translated from here to here, we said, oh, this is what's happening in the original frame. And I am running along at V0, so then I see this. Now in this case, if I'm running along at V0 in this case, and this is what I see. Then from a person on the ground, it looks like 2V0 and 12 minus 2V0. To check this, just like imagine that this is the ground frame, and I run along at speed V0. What do I see? Well, it looks like the 4 kilogram is only moving at V0 away from me. And it looks like that this thing is actually moving faster away to the left out by V0, so 12 minus V0. So the point is that we sort of use the center of mass frame to sort of help us, but what we got is that at the end, the system looks like this in the original frame. This is in the original frame. So this is the diagram in the original frame. And then by using the center of mass frame as an intermediary, we just see that this guy goes from here to here, where V0 is the center of mass velocity. And then in the problem, we're given that 12 minus 2V0. We're given that this velocity to the left is just 6 meters per second. So that means that V0 is 3 meters per second. So this is a kind of, if you haven't seen this idea before, it can be very confusing, especially translating between frames and getting the right answers for the velocities in the new frame of reference. But practicing this is good because then collision problems become a lot more intuitive. And you can sort of like, if you're familiar with this, then you can sort of very quickly just do these steps and just say that, oh, like just solve 12 minus 2v0 equals 6 directly and get v0 equals 3 without having to set up a much more complicated system of equations. And generally, like, there's more applications to this than just simply saving a little bit of algebra. In some cases, the algebra you have to do in the non-center of mass case is much more complicated. And an example of this is problem 7. So we probably don't have time to get to problem 7. It's a 2D collision problem. But think about the center of mass idea for problem 7. Because without the center of mass idea, problem 7 is extremely nasty. Lots of trigonometry, lots of complicated expressions. But in the center of mass frame, it's a lot more doable. Problem 7. All right. So for sake of time, I'll skip problem 3. But problem 3, it's a sort of tricky problem because it's a very complicated process. But if you think about it, almost all the forces in the problem are internal. So there's a sort of global momentum conservation that happens because a lot of the complicated sliding and slipping in the problem is all internal forces. So that's my sort of hint for problem 3. And you can sort of solve it using the ideas we've said. So let me go over problem 4 now. I think problem 4 is a very important problem because it sort of deals with this idea of impulse. And it seems like people have a lot of questions about impulse and instantaneous impulse. And problem 4 is dealing exactly with that kind of thing. So by the way, any questions about center of mass things? Now, if you haven't seen it before, I can see how sort of getting from here to here is very confusing and getting from here to here is very confusing. But think very carefully about frame of reference changes, and you should be able to derive these results. So any questions about the sort of center of mass idea for collisions?
So is this something like looking at a ball rotating from its center?
Sure. I don't actually know what you mean by looking at a ball rotating from its center. But like generally looking at things in the center of mass frame, things become simpler. So somebody's asking, how did I get from here to here? So the reason is that this picture is in the center of mass frame velocity. So in the actual picture, in the actual frame, if this thing is moving to the right with v0, then in the original frame it must be moving to the right with 2v0. Because if I imagine then moving along with the center of mass, which is at v0, then this block looks like it's only moving at speed v0 to the right, which is what I see in the center of mass frame. And similarly, if I'm running with v0 to the right and I'm seeing sort of 12 minus 2v0, then if I'm running with v0 to the right, then it actually looks like it's moving backward to 12 minus v0. Like it's moving faster to backwards to the right. To the left hand. So the way, like, it's maybe easier to think about going from here to here, or if I transform to the center of mass frame, the frame moving at velocity v0 to the right, then the picture transforms from this to this. Again, have I considered center of mass always moving with v0 to the right before and after the collision? Yes, this is what I said at the very beginning. The center of mass velocity is always the same in a collision if there's no external force. There was no external force in this problem. The center of mass velocity was always the same, v0 to the right, because there is no external force. Yeah, exactly. So the surface velocity is like undoing the CM frame, right? It's like going from backwards from the second step to the first step. Exactly. So if you understood first step to second step, then first step to second step is the same as going from final step to third step, because both these are sort of going from original frame to CM frame. Or you can think of it as going from here to here as undoing the CM frame. But I think if you understood the first to second, then the last step should also be basically the same thing. It's just sort of going backwards, so it may be a little bit more confusing. But it's essentially the same idea. Really good questions, by the way. Let's give it like 30 more seconds, and if there's no more questions, then move on to the next problem. All right, let's move on. So problem 4 is a very interesting problem. Okay. Could you please, we're going back. Could I please share these handwritten notes along with the session recording? Sure. I mean, hopefully the session recording has these handwritten notes in them, but I'll share these notes as well. But these are not very good notes because I'm sort of using it as a whiteboard to just write on. So don't take these notes to be too absolute, but sure, I can share these as well. All right, problem 4. I'm frozen. Am I still frozen? Hello? Hello? I'm frozen. Okay. Huh. Well, let's just give it a few seconds to see if it catches back up. You can hear me. Everything's good. Okay, great. Good stuff. All right. So problem 4. You have incline of angle theta. You sort of have this little block, that's M, which you sort of drop. And right before it hits the, or let's actually draw this, like you have a block and you're dropping it like this. And right before it hits the thing, it has speed v downwards. So you dropped it with some height, and right before it hits the inclined plane, it has speed v. Now, once it does it, it sort of hits the sort of inclined plane, and then starts sliding down. So what is the new velocity so you can phrase this very sort of cleanly using impulses, but the concept of instantaneous impulse is very confusing to many people. So we're actually going to do this problem with forces and then turn it into impulses. So we're going to do it in a sort of more correct way, where I use forces and then sort of convert those into impulses, and then everything should be clear if you know how forces work. So the question is, what happens in this process as this thing falls on to the inclined plane? What forces are acting on this object as it falls on? What forces? Normal force, good. Gravity, good. And friction, very good. And what happens is that these forces need to change the momentum from this is the original momentum, to something like this. The forces have to change the momentum from this to this, which means they need to apply some force. And then they apply it over some period of time, there's some impulse, and they change. So let's think about it. What happens to the sort of, if I define x and y to be like this, what happens to the y component of the momentum? Yes, somebody gave the idea in the chat, but let's wait for a couple. So what happens to the y momentum of the block? It originally had some y momentum, and again, y is not parallel to the ground, but it's parallel to the inclined plane. So n equals mg cos theta is not correct, and the reason for that you'll see why. So let's say that a process happens over time delta t. So basically what's happening is that the change in the y momentum is p0 cos theta. And the forces in the y direction so hopefully this is just saying that this equation is just saying that the y momentum gets killed completely by the forces. And the equation about the x momentum is saying that sort of p0 sine theta minus p1 equals this is y momentum change, and this is x momentum change. So I went a little bit fast, but the point here is that the original y momentum is p0 cos theta down, and it becomes 0. So the overall change is p0 cos theta, and the forces in the y direction is n minus mg cos theta, and acts over time delta t. And similarly here for the change in x momentum. Now, in this process, is static friction being employed or kinetic friction being employed? Can somebody tell me? And can somebody give me a reasoning why? Kinetic, but why? So the reason that the way to tell the difference between kinetic and static is that the exact way to tell the difference is what is the relative velocity of the point of contact with respect to the ground. If I have a block sliding, the point of contact with the block and the ground is moving, so it's kinetic friction. In a rolling wheel, the point of contact between the wheel and the ground is fixed, so it's static friction. If it's just a stationary block on an incline, the point of contact between the block and the ground is 0, below 0 velocity, so it's static. Here, this block starts with some crazy velocity here, and it's sort of very fast for moving its velocity this way. So it's the point of contact, the relative velocity is v, or it's non-zero. So why I take p1 considering p0 exists? Well, p0 sine theta is the original x momentum, but there's all these forces could be changing that x momentum. So the final p1 could be something different. Also, perhaps I got this right. The final x momentum is not just the same as the original x momentum. It's being acted upon by friction and gravity. So there's no reason it should be the same. Now, somebody brought up a very important point. shouldn't the static versus kinetic not matter since coefficients for both are the same? That is wrong. Even though the coefficients are the same, it matters whether it's static or kinetic. The big reason for that is here's the friction side. In static, all you know is that the friction force is less than or equal to n mu. In a static friction problem, you could have zero friction. For example, a block sitting on a horizontal table. There's no friction because there's no sort of gravity pushing it in the x direction. But you might say, oh, there's a normal force mg, so shouldn't there be an n mu friction force? Well, that's not the case. If I just have a block sitting, then I have n, I have mg, and I have no friction, even though it's a static friction with coefficient mu. So how is that possible? Right? So the reason for that is that in static friction, all you know is that F is less than or equal to n mu. But in kinetic friction, you know F is always equal to n mu. So that's the big difference. Even though the mu's are the same, in static friction, you don't actually know that the frictional force is the same as n mu. But in the kinetic case, you know it's the same. That's how kinetic friction works. So this is a very important point of confusion that happens for a lot of people. But hopefully this clears up something about friction. So because in this problem, it's kinetic friction as we established, we know that F is equal to n mu because it's kinetic friction. So I can now write P0 cos theta Now here's a very important point where we sort of talk about small times and large forces. So this delta t is very small because this block over almost instantaneously goes from speed v down to sort of down the incline. What that means is that n must be very large. N minus mg cos theta must be very large. Delta t is very small. But if you think about it, mg cos theta is always a small number. It's always a finite number. Excuse me. A bounded number. It's just mg, at most mg. And mg acting over a very small time delta t is negligible. But since n could be really huge, normal forces are things that can be very large. And in particular, the reason they can be very large is like if I have a table and I drop a really, really, really heavy object onto a table, the table breaks. Why does the table break? When I drop a really heavy object on a table, why would it break the table? Well, the reason is that the table is trying to provide a really large normal force so that the impulse from that normal force sort of slows down the object and makes the object just sit on the table. But if that object has such large momentum coming into the table, that the amount of normal force needed to over the short period of time to sort of make the object come to rest is extremely large.
40.
So if I have a really, really large, a really heavy object, like some really, really heavy bowling ball, and I drop it on a table and it breaks the table, that means that it's because the object had really large momentum. Then the table would have to provide a really large normal force over a short period of time to stop the object. But if the table is just not strong enough to provide that normal force, it breaks. But yet, yes, friction is also large because friction is n mu. So if n is large, then friction is huge as well, which is perfectly fine. But the point is that mg is negligible compared to these really large normal forces and friction forces. So we can essentially, since delta t tiny, n and f huge, mg is negligible in this context. And this sort of makes sense. If I have a really fast collision or really fast thing where the block goes from sort of going down to sort of going down the plane, gravity should not be relevant because gravity is a force which acts over like a longer period of time. Over a very instantaneous sort of collision, gravity is not relevant. And it's for this reason exactly. Because the gravitational force is always going to be a sort of bounded number. And if I multiply it by a very small delta t, the impulse from gravity is negligible. But the impulse from these really, really large normal forces is relevant. So then I can sort of rewrite this as P0 cos theta is just, I'm going to write it as J sub n. It's the impulse from the normal force, which is n delta t. Equal to J sub f, which is equal to mu times J sub n. And this is equal to f delta t. So the reason we can ignore mg in this case is because it's acting over a really short period of time. The thing is here is that the impulse is happening over a really short delta t, which is why the mg provides negligible impulse compared to normal forces and friction forces. Anyways, now if I solve the system of equations, I just get that P0 is Jn over cos theta. So Jn tan theta implies that P1 is equal to Jn tan theta minus mu, which is just equal to so which means that the P0 was equal to mv. So the final velocity, if I sort of say mv1 equals mv, I'll write this as sine theta minus mu cos theta. So the final velocity is and again, somebody brought up the point of why is this number not simply just v sine theta, right? If we just had P0 sine theta, why is the final exponent not just P0 sine theta? Well, if you look at this example, the final answer, if I set mu to be 0, then it is just v sine theta. It's literally just the original v in that x direction. But since there's friction, which is exhibited by mu, it's become less. So this is a very, very important example about how impulses and such work. Any questions about this? About friction, about impulse, about anything in this problem? This is a very important example. Yeah, I agree. It's a very nice problem. This is from the USA Physics Olympiad in 2018. So the first problem on this one, this is the 2018 USA Physics Olympiad. If you're curious. Quite simple to understand for a useful problem. I claim most useful problem solutions, if I present the solution, it's not going to be too complicated. I think this problem is quite tricky to solve, though, because understanding that the friction is equal to n mu and all the impulses, and thinking about impulse in this very concrete way, and understanding that the friction force provides a large impulse, and the gravity doesn't, and then setting that the frictional is always equal to n mu because it's kinetic. Because if you don't know it, if you know that it's static, then you don't know that f equals n mu. That's a very subtle point that a lot of people miss. Please mute whatever that is. So yeah, but it's a good problem. It's a nice problem which demonstrates some concepts. Any questions about this one? So just if you didn't understand the quite last few steps, then just look at the recording and try to see again. But is there any concrete questions that you have about any of the steps? And yeah, I understand. I went very fast. I completely agree. But just for the sake of time, just go back and re-listen to the recording or look at the notes or something. Or you can also go read the solution on the website, the APT website. Okay, let's finish with one final problem, and then we'll stop for today. This is problem 5. So this problem, what we have is we have a sort of heap of chain, and I have a little piece of the chain coming out, and the chain is density sigma kilograms per meter. And then I sort of hold on to this end and pull it with a force F. And as I pull it, this sort of chain unravels and pulls out of this huge heap of chain. So the question is, if I do this process, what is the position of the end as a function of time? So let's think about this problem. So at a time t, what is happening is that you have xt of the chain, you're pulling at F. So what's the sort of object that you're pulling? You're sort of pulling this much of the string. The mass of that piece is sigma x, and the velocity is x dot. So the momentum is sigma x dot of the piece that you're pulling. And we know that F equals dp dt, which is equal to, by the product rule, sigma x double dot. And note that this term right here is the ma term, because m is sigma x and x double dot is the acceleration. But because the mass of this piece that I'm pulling is changing, I also have an extra sigma x dot squared term. What are the dots? Okay, dot is a very common notation in in physics. It's just y dot is dy dt. It's like prime in calculus, but dot usually represents time derivative. Does that make sense? Sigma x dot squared. That's just by product rule on this. So if you're not too familiar with calculus and stuff, then this problem will be a little bit hard to follow because it uses calculus decently. But I'm just using the product rule on this one. Okay. Now this is a little bit complicated to solve. This is differential equation kind of thing that we end up getting. But a sort of simpler way to do it is we know that F is constant. We're pulling with constant force. which means that we know that the momentum grows linearly as a function of time. Just if I just look at this equation, then if f is constant, because f is constant, that's what the problem tells us. We're pulling it with a constant force. The momentum is just a function of time like this, which means that sigma x dot is equal to p. Is equal to ft. And I can rewrite this as sigma x dx dt equals ft. So I can rewrite this as sigma x dx equals ft dt. And if I integrate this, then I get 1/2 sigma x squared implies that x is which means at the end of the end of the chain moves at a constant velocity in this case, which is quite interesting. Normally, if you pull at an object with a constant force, it moves with constant acceleration. But in this case, due to the fact that the mass is changing and all that, it actually ends up moving at a constant velocity. What is use of sigma x dot squared? I just did the product rule here. I literally just did p equals sigma x dot and did the product rule. And the reason it's there is because if I have a changing mass system, then the force is different because the mass is also changing. So you have a v times dm by dt term in the force. The way to think about it is that if I have a system and I'm adding mass to it, then I have to accelerate that mass that I added to the original speed v that the system is at. So that's why there's a sigma x dot squared. So the reason I didn't use it anymore is because in this case, there's a simpler way to solve it where you just notice that the P is Ft. So that's why we don't need to sort of use this method. We can just say that the momentum is just growing linearly with time. So in this case, we could solve it simpler. But if you want to, you could sort of view this as some sort of complicated differential equation where f is constant and try to solve it using that. But in this case, there's a simpler method. Any more questions? Momentum is not constant. Momentum grows linearly as a function of time. Because f is constant. That's what we're given in the problem. And we know f is dp dt. So the momentum grows as ft. And then you can just use that to solve the problem very simply from there without having to do this differential equation kind of thing. So the end result is very fast that we pull it out with a constant force, but it ends up coming out with constant velocity. And the reason for that is because we need to sort of accelerate the extra. The way to think about it is that when I pull a little bit, then a little bit extra mass comes out from the heap. And not only does my force have to accelerate, not only is my force sort of having to accelerate the piece that's already the pieces that are already there, but it has to sort of bring that new piece of chain up to speed from 0 to the speed that this thing is moving at. So that force has to also be used to accelerate the new mass that's being added in. That's why the force is different when you have to add new mass, because you need a force to accelerate that new mass that's being added in. And mathematically, this is what it is like. All right. Any questions about, so that's basically all for today. If you want to leave, then feel free to leave, but I'll just stay for a few more, like 2 more minutes to see if there's any questions about anything that we talked about today. You're welcome. Yeah. Where can I find answers to the problems? Well, most of the problems are from either F equals ma or USFO, which means that you can look them up on AAPT. And these problems, these last 3 problems are from David Morin's textbook, and their solutions are available in that book. So if you have David Morin's classical mechanics book, which is a book I recommend that you get. It's a very good book for mechanics. The solutions are in that book. But depending on what happens, I may also send a solution PDF, but I'm not 100% sure about that. All right, if that's all, if you're having trouble understanding the problem statement, which problem are you having trouble understanding the statement for? I mean, in general, if you don't understand the statement of the problem, then either you don't know the material which that problem is like talking about. Like it generally comes with experience. So a lot of times I agree with problem 4, it's not exactly clear what the problem is talking about. But if you've seen problems like it, then it's sort of it becomes more like I don't have a good answer to that off the top of my head. In general, if you do a lot of practice, you should be able to understand most problem statements. But the answer is just to do more practice. If there's a problem which you can't understand the statement for, either ask somebody about it who knows more physics than you, or just move on and just do more practice in that area, and hopefully you'll be able to understand it afterwards. But there's not a good general answer to that. All right, let me stop the recording as well.